Hello, everyone, and welcome to the Insights in QA webinar for our recently published report, Powering the Future with Energy Storage. My name is Sapar Magari, and I'm the Battery and Energy Storage Lead at CICE, BC Center for Innovation and Clean Energy. And joining me shortly is our research collaborator and the author of the report, Michael Delage. But before I begin, I just want to cover a few housekeeping rules. This webinar is being recorded, and the slides and the video will be shared afterwards. There were some questions that were raised during registration, and we've done our best to address them in these slides. But if you have any questions, please feel free to put them in Zoom using the Q&A feature, and we'll take those questions at the end. I want to acknowledge that CIC operates on the traditional, ancestral, and unceded territories of Musqueam, Squamish, and Tsleil-Waututh nations. CIC is an independent, not-for-profit organization founded in 2021 to catalyze seed investments in early-stage clean energy innovation, where often the lack of customer validation and revenue is a barrier in reaching the market. We aim to be at the forefront of scaling BC's innovative solutions and enabling a world-class clean energy sector. CIC is committed to fostering the widespread adoption of clean energy solutions across various industries. We operate in 4 strategic focus areas: carbon management, low carbon hydrogen, low carbon biofuels and synthetic fuels, battery and energy storage. To date, we have invested more than $23 million in technology and clean energy projects across these focus areas. And those projects have been able to raise a total of $145 million to complete. That's almost a leverage of 7-to-1. These investments have supported more than 30 innovators, and some have been able to raise additional funding and global recognition for their leadership and ingenuity. For a complete list of innovators and projects, please check our website. What really sets us apart is our unique approach of using intelligence to guide investment decisions. And this report is a good example of such intelligence work, where it was really important for us to identify the opportunity and the role of energy storage in enabling electrification and grid decarbonization. Michael Delage was instrumental in producing this work, and there's a short bio of him in the report. We had to make the bio short because otherwise the bio would have been longer than the report. Michael is an accomplished and experienced engineer, executive, and an entrepreneur. Every conversation with him, I learned something new, just an incredibly smart individual and a pleasure to work with. Michael, please take it away.
Well, thanks, Seb. It really was a privilege to work with the knowledgeable team at CICE and yourself, and it's been a really great experience working on this. Okay, so next slide, if we get onto the focus here. The report, and we're going to touch on really 4 kind of areas today. The report is about energy storage, but it's about energy storage in a given context. And that context really is trying to understand the role of energy storage and how it will change or how it participates when we look at the increasing penetration of renewables into the electricity system, and the role of electrification and how electrification of some key sectors will change the grid and therefore the role of energy storage. So from there, we can look at actually those roles of what energy storage can do on the electricity system. And it's a variety of different applications for energy storage, and that really depends on kind of the grid and the jurisdiction. And then from there, we can touch on the different technologies involved. And of course, there are going to be lots of discussion around batteries, but it's about a lot more than batteries, especially as we look forward. And finally, of course, this is a British Columbia-centric report, and we're very keen to look at and report on kind of both the demand side and where energy storage fits in British Columbia's needs, but also as innovators in British Columbia, where are the strengths of British Columbia and where are the opportunities that it can take advantage of to participate in this sector. Next slide. Go ahead. All right, so renewables have really changed the electricity generation market substantially, especially in the last 10 years. If you look at the drop in costs for photovoltaics and for wind, they've come down dramatically, 8 times in the case of solar, more than double in case of wind. And consequently, and probably to no surprise, along with policy support, we've seen really rapid increases in penetration with, again, an order of magnitude increase in solar, doubling of wind penetration in terms of worldwide capacity. And if you look locally in certain jurisdictions, you see much more rapid increases in penetration of renewables. And look at places like California and Texas, which effectively had no renewables 25 years ago, and now they exceed 25% of the energy that it's providing to those. And it's really hard to keep those statistics up to date because it is continuing to increase so quickly. Next slide. The thing is that renewables, as we know, have quite different characteristics as opposed to traditional generation, which operates kind of when we want it. Renewables are characterized especially by their variable supply, that they provide energy when the environment is conducive to doing so, whether it's when the sun is shining or the wind is blowing. And as a consequence, that means that generally the capacity factor for renewables is relatively low. The percentage of the time when they are producing electricity is 25% or 35%. And that means, of course, there's a lot of time when they aren't producing energy. However, they also characterized by some different things which are really important in terms of the market. One is their cost profile. The cost of producing energy in terms of operating costs for wind or solar is essentially zero. These are essentially CapEx investments, and once built, because of their low OpEx, the price of the marginal cost of electricity they produce is very low and can be actually bid down to almost zero. And the last thing that's quite different from traditional generation is deployment scale. Even wind turbines are sort of at most 15 to, now they're climbing to 18 megawatts in size. That's much smaller than, say, a large nuclear plant or coal plant, or even combined cycle gas plants. And that allows for renewable generation to be located in a lot of different places within the electricity system. We're familiar with rooftop solar penetration in some jurisdictions, but really it means that not only are these going to be located at the end of major transmission system connections, but they may be located just about everywhere on the grid. And that changes how we think about electricity flows and how the grid operates. Next slide. So the consequence of that zero marginal cost of generation is that what we see in, especially in open electricity markets, but even outside or in traditional regulated markets, is you see displacement of traditional generators. If it costs nothing to produce solar or very little to produce an incremental solar kilowatt hour when the sun is shining, then you're not going to run a gas plant and pay for gas when you could just use that essentially low cost solar. And so if you own a solar generation plant in a market context, you're willing to basically bid the price down to almost zero. As long as you make something, it's still better than nothing. And so you see that when the renewables are available, they displace conventional generation. Of course, when they're available, and there's a lot of them, they can outpace the need for electricity. And so you do see increases in curtailment as renewable penetration goes up, even when we're only dealing with overall penetration of renewables that's less than 50%. And that penetration, importantly, is not just a system-wide issue. It's not just when the whole system has more electricity than it needs, but it's often due to local factors where the grid is just not set up to be able to move, say, rooftop solar from one neighborhood to another one where there is a demand still to be met. And if you look at places like California, up to 2/3 of curtailment is actually driven by those local conditions. And that's really important when you think about distributed generation. Because it's displacing natural gas, and you see increased cycling of those systems, and they cycle more often, which actually is not as good for especially combined cycle systems, but it also means they operate less often. So you see falling capacity factors for traditional generation. When they operate less often, that also impacts their economics. There's fewer kilowatt hours being generated to spread their annual fixed operating costs over. And so as renewables increase in penetration, not only do their volumes mean that their costs come down, but it means that the costs of conventional generation also go up. And as a consequence, when you look at the way markets operate, you're going to see a split. Instead of sort of average electricity prices, now you're going to see a bimodal distribution where renewables are available and there's a lot of supply. Prices decline to very low levels. And then when you have gaps in the renewable availability, when you have shortages in sun or wind, that's when you see high price spikes, because the renewables have crowded out the conventional generation that is going to meet the gap at that point. And as a result, the demand is going to be very high on that, and prices will rise as a consequence. So a very different market to what we're used to seeing in the electricity system. And if you look at California and Texas as good examples highlighted in the report, you see the effects of that, whether that's the duck curve that a lot of people have looked at in California, where you see the price of electricity drop to near zero, or the net load drop to near zero when you have a lot of sun. Or in wind dominant Texas, where you see a lot of natural gas cycling as a consequence of wind availability, and you've seen a considerable decline in coal use. Next slide, please. All right, so the other major kind of macro factor affecting the market for energy storage is electrification. And really three big areas that we're looking at electrification. One is industry. And EIA projections are for significant increases in electricity demand for electrification. Industry use is really in an all time, all day, all times of the day, 24/7 type of increase in use, generally a sort of overall increase in energy consumption for electricity. But transportation and heating are a little different, and their impact's important because transportation is very cyclical in terms of the times of the day when you're going to see people charging electric vehicles. So that can create an increase in daily peaking. And heating is the same thing. When you talk about electrification of heating, you look at two big impacts. One is, of course, daily cycling of demand. And as you get into the evenings, the demand for heating goes up, so it increases peak demand. But also the transition of a lot of jurisdictions in terms of electricity use from a summer peak to, as they electrify heating, they may turn to a winter peak. And so that is going to change the dynamics of those electricity systems, where you see different fits in the types of generation they may require as they move from summer to winter. Next slide. So here's a good example of how that impact plays out. And again, looking at a kind of duck curve in California, you can see with electric vehicle charging, if it's unmanaged and everybody comes home in the evening and plugs in and expects their car to charge, you can see a big increase in the peak demand in the evening. So there's a big increase in that cycling. But the other thing that's really important is just how big the ramp is. The slope of that curve becomes a big point of stress on the electricity system. And managing that through various programs, whether they're sort of passive, like time of use rates, or active in terms of charging control timing, is going to be really important as we look at electrification of EVs. But it also speaks to opportunities for energy storage. Next slide, please. Okay, so in that context of change, what are we seeing in terms of opportunities for energy storage? Well, the biggest one and the kind of obvious one is to think of time shifting energy. If you're an engineer, you think about, okay, well, we have sun during the day, but we need electricity at night, so we're going to charge up a battery, store it, and discharge at night. If you're an economist, you say, well, during the day we have too much energy and the prices are low, but at night there's not enough and the prices are high. So this is an arbitrage opportunity. I can buy low and sell high. And so energy arbitrage is really the number one application when we think about energy storage, and that not only on an hourly or a daily basis, but as we'll see, it goes into longer term. And energy arbitrage is true whether we're going to talk about a bunch of other applications, but this is always there. You're always needing to charge and discharge an energy storage system. And so that delta in prices is always going to be part of the economic model for an energy storage system. The second thing is peaking capacity. And it sounds like it may be the same thing, but really the difference here is one of decision making. So is the energy storage system owner deciding purely based on price when they're going to charge and discharge, or are they making themselves available as a resource to the grid operator to be called upon to help meet peak demand at given times of the day? And then lastly, and kind of wrapped in on this, is you see increasing amount of energy storage systems being built paired with new renewable generation. And that's because capacity markets operate in a lot of places where generation is paid to be available when needed. And it's very difficult for renewables on their own to participate in capacity markets because there's a lot of uncertainty as to whether that renewable generation will be available at that particular moment or not. But when paired with energy storage, it firms that, and the combination of energy storage with renewables allows for participation in capacity markets as a revenue stream. Next slide, please. In addition to those sort of big picture time shifting energy applications, you look at a variety of other services can be provided. If in terms of behind the meter, if it's residential, commercial, or industrial, your applications include not only those energy arbitrage, but also grid bill management. If an industrial or a commercial application may be subject to demand charges, and energy storage systems can be used to reduce peak demand and reduce demand charges, as an example. Ancillary services has proven to be a really important energy storage service early on here as we look at deployments on the grid. These are things like voltage management or frequency management, very fast response from energy storage system to charge or discharge in response to spikes in demand or drops in demand on the grid. And battery energy storage systems, as they've been deployed, have proven to be very, very effective in providing ancillary services. These aren't necessarily the deepest of markets, and you think about the amount of energy storage that might go on to a grid, the amount that would be able to generate revenue from ancillary services is going to be saturated at some point. But nonetheless, it's been a really important opportunity, and certainly an area where energy storage has proven it can outperform conventional generation in terms of gas turbines. And then lastly, we see increasing applications for energy storage in transmission and distribution network support. As we increase renewables, and renewables are generally located maybe not close to centers of demand, we see increasing demands for upgrading transmission capacity. And one way to get more out of existing transmission capacity is to put batteries on either end of a transmission line. And then when the transmission line is not at peak capacity, it can be used to move energy down the line from one battery system into another, from a location far away from demand where it's charged during the day when solar is available, move down the line to a battery system that is close to the center of demand, where it can be discharged in combination with the transmission line to meet peak demand. And in that way, utilities can offset investments or delay investments in major upgrades in the grid. And the same thing is going to be true as we look at loading onto the distribution network. Next slide. So those are sort of high level things. As you start to get into each of these applications, and the report talks about this, the exact requirements when it comes to energy storage systems in each of these applications is going to be slightly different, whether it's the durations involved. Something like frequency management is very fast, short duration storage, whereas time shifting renewables for sort of seasonal uses is going to require very long duration storage. And it's not only the duration of the storage, but the power levels, voltages, and so on, which change as you look at these different applications. And important to think about is each of these applications are not to be serviced alone, that an energy storage system can often do many more than one of these at a given time. And the next slide, please. And if you look at examples from, say, again, California, you can see how revenues for energy storage systems in the California market are coming from a mix of energy arbitrage and frequency regulation and reserve capacity. And it's that combination and that collecting of different multiple services which really builds the business case. And this is really important to realize, because if all you do is look at one aspect of energy storage and in one application, the business case is not really going to be reflective of what the potential is of energy storage on the grid. And that's important whether you're a supplier making the business case, or you're an end user or utility that's contemplating the deployment of energy storage. It's really, really important to look at the variety of different services that system can provide and the value it can provide to do fair justice to that opportunity. Next slide, please. All right. As a consequence of what we've seen, it really and these different applications that energy storage has proven to be very good at, in addition to electrification and advancement of renewables, we've seen rapid growth in deployments, especially, to be honest, in the form of lithium batteries, and that comes large part due to the decreasing cost that's been driven by the electric vehicle market. And grid-connected energy storage is about 1/10 the size of the electric vehicle market. So the volumes from EVs have really helped the deployment of lithium batteries on the grid. But we've seen just tremendous growth. And these are 2022 statistics. If you look at 2023 and forecast to 2024, that exponential curve is continuing to grow. And so, and it's not just in North America, but it's worldwide. And so we've seen a really, really tremendous takeoff in this market. And it's one of the reasons it's such an area that's interesting. Next slide. Because the market today is going to change. Today's short duration lithium batteries, which are sort of short duration 2 to 4 hour, maybe pushing up to 8 hour energy storage systems, is adequate for helping to manage renewable penetration, where we see shifts that are really on that daily basis. Lots of sun in the daytime and trying to help carry that energy into the evening. But as we try and move towards increasing penetration of renewables, and we're going to go there because renewables are the lowest cost form of new generation right now on a per kilowatt hour basis. So this transition is going to continue, at least for the foreseeable future. But the duration of energy storage that's required as you try and get to increasing penetration of renewables, the grid goes up. So you go from hourly energy storage to daily or weekly, potentially even to seasonal energy storage. And as you move towards longer and longer duration energy storage, the costs necessarily have to come down. One way to think about that is a energy storage system which charges and discharges on a daily basis gets to sell its capacity into the market once a day, 356 times a year, or 365 times a year. That something that is weekly or monthly gets to sell its capacity only 50 times or 12 times a year. And so per kilowatt hour, the value of that capacity, or the cost of that capacity, has to come way, way down in order to be a profitable investment. Next slide, please. And that's important because it ties into technologies. And as we think about the technologies that are available today and the market that's going to be necessary as we go to higher and higher penetrations tomorrow, we may see a shift going on. We've talked a bit about batteries, and lithium batteries today truly do dominate the energy storage market, at least in terms of what's being deployed. However, if you look at the total energy storage capacity that is existing in the grid today, pumped storage hydro really is the incumbent. And that's because it's really hard to match the scalability of pumped storage hydro. You can build gigawatt hours of capacity in pumped storage hydro systems. The technology is well understood and proven. And so really, as we move towards longer and longer durations, it is still going to be pumped storage hydro, which is the incumbent. Now, it can't necessarily be used in all places, and it does face restrictions in terms of location on the grid. It can't be as close to centers of demand necessarily, but connected through transmission systems, it will still be likely a large participant, and we do see that in the rates of deployment. But it's not the only technology. If we go to the next slide, we'll talk a bit about lithium. And so lithium is the dominating technology in the market today, and it is continuing to decrease in cost. And this is really, really important because of the rapid amount of innovation and increases in energy density and power density driven by the electric vehicle market. The costs are still continuing to come down at a fairly rapid rate. And if you're a technology innovator and an innovative technology provider looking to compete with lithium ion, you really have to understand not only what is the cost of lithium ion today, but what is it going to be in 2 years or 4 years, or the time that you're able to achieve commercial scale. Because that's really the bullseye that you have to be aiming for, is to be sure that you can be competitive with lithium ion in the trajectory that it's on. That said, despite those continuing decreases in costs, when we start to think about long duration energy storage, the multi-day or weekly that's necessary to support high renewable penetration on the grid, it does look unlikely like lithium ion is going to be able to get to those cost levels. We're talking about decreases maybe 50 times below where lithium ion is today in order to be viable as long duration energy storage. And that does look like a stretch. And that means there's an opportunity for new technologies to step in. Next slide, please. This is just sort of some data that's in the report kind of backing up that trajectory of lithium ion, that energy density and cost. So it's not just a manufacturing scale, it's an innovation effect as well that are driving costs down, and lower costs mean higher demand from an economics point of view. So the opportunities for lithium keep growing. And this is not a trend that's necessarily going to slow down anytime soon. Next slide. All right, so what are the alternatives? The alternatives are things like flow batteries. So flow batteries are ones where you're able to store the energy and the electrolyte and it can be scaled separately from the size of the electrodes. And this is really kind of an important advantage, is that the power capacity of a flow battery can be controlled differently from the total storage capacity. And that allows it to be tuned for different applications. And it also potentially allows for the ability of flow batteries to come back and be upgraded to increase capacity, to increase the storage duration down the road. The two most prominent flow battery technologies are vanadium and zinc bromine. Although there are some others, they're certainly the ones that are first out of the gate, and we're seeing kind of early commercial deployments. A challenge there is to see how can they get to scale. Additional technologies include metal air batteries. There's been a number of bigger announcements in terms of new companies and startups in the metal air battery space, such as Form Energy. That's an iron air battery. The potential there to be very low cost. The trade-off is generally efficiency suffers. And so when you look at long duration energy storage, you're willing to make some compromises on round trip efficiency. You know, how much energy you put into the battery compared to how much you get out of it, in order to hit the low cost profile needed for long duration energy storage. And then there's some other technologies that are worked on. Sodium ion is seeing a fair bit of growth right now because it avoids some of the potential constraints in terms of supply chain availability of minerals that may be an issue for lithium as the market continues to grow. There are other battery technologies such as variations on zinc and nickel hydrogen. And then there are other technologies which really are kind of part of the solution, like supercapacitors. In all likelihood, you know, they may be combined with batteries to provide grid services, but they really have a big advantage when it comes to the very fast cycling applications such as frequency response and voltage support. Now, all of these have similar sorts of things that give them an advantage in the long term over lithium ion. In terms of addition to critical minerals or lack of dependence on critical minerals, much lower safety concerns related to fires and fire risk. The challenge is they need to win scale, and they may be good technologies for very long duration energy storage, but the market isn't there yet in terms of long duration energy storage. There's nobody buying sort of multi-day or week-long energy storage systems yet. And so the challenge for a lot of these technologies is how do they win business in that intermediate stage? How do they compete with lithium ion in the 8 to 10 to 12 hour market in order to gain scale and get on a learning curve so that they can see their cost profile start to decline, like the way lithium ion batteries have seen their cost profile decline. And that'll be an interesting challenge. It's an area where innovation can play a real role as well. Next slide, please. If we could look at non-battery technologies, there's some important ones as well that are being contemplated. So electrification of heating, both in building heating systems, but also in industrial heat use, is an important area for decarbonization. And anywhere you have use of heat as an end use on its own, as opposed to, say, converting back to electricity, you're probably going to see an opportunity for thermal energy storage. And that's because the charging of a thermal energy storage system is almost 100% efficient. It can be more than 100% efficient if you use the heat pumps at lower temperatures. And the storage mediums are generally very low cost. And so the cost of storing energy as heat, if you're going to be generating that heat from electricity anyway because of electrification, the cost of storing that energy as heat is going to be a lot lower cost than storing it as electricity. And so anywhere you see energy store or thermal heat energy used as an end-use application, you're going to probably see opportunities for thermal energy storage. Converting back to electricity is going to be more of a challenge from a market point of view because the efficiency on that side really does suffer unless you get the temperatures way up, and that brings in other technology challenges. Compressed air and hydrogen are other ones. Compressed air is probably the most direct competitor potentially to pump storage hydro. You're looking at large underground reservoirs. Ideally, above ground compressed air storage tends to be more expensive because of the cost of the tanks. But if you can get the geology for below ground energy storage, then compressed air may be an option. Compressed air really is kind of a mix. You think of it as a mechanical energy storage mechanism, but it's a split between about half the energy is ends up being stored as heat. When you compress the air, it gets hot. You need to store that heat and then recover it when you're discharging in order to make that viable. Hydrogen is the other opportunity here. And again, this is probably going to be driven, especially where you have end use applications that need hydrogen as a feedstock, as we look at electrification of concrete or heat or steel making or other industries like that. Then hydrogen is a really important way that we can transition those industries to decarbonize. And there's probably where you're going to want to look first for hydrogen energy storage, because again, the conversion of electricity into hydrogen isn't terribly efficient, and the conversion back to electricity isn't terribly efficient. And so as a pure grid energy storage mechanism, it's going to be more difficult to compete with batteries or pump storage hydro. However, where you need hydrogen anyway as an end use, there are going to be opportunities for energy storage. All right, next slide, please. We talked a lot about the underlying energy storage technologies, but one of the things that's also important to realize is that a lot more goes into an energy storage system than just the core energy storage medium or the storage block. It's much more than just the battery. There's a lot of other equipment, and there's a lot of other costs and therefore economic opportunity associated with that other equipment. The balance of system, whether that's thermal management systems, power equipment, communications and control systems, these make up meaningful portions of energy storage systems, and there are opportunities in those for innovation. And one that we kind of highlighted in the report in particular is looking at power conversion equipment. As you get to increasing amounts of renewable energy and you start to displace conventional generation, what you see is a loss of what's called inertia on the grid. And this is one of the ways that the grid maintains stability right now. And so improvements in inverter technology that allow for, whether it's renewables or battery storage systems, to fill that role, to provide those fast response services, to establish the voltage and frequency on the grid instead of just following the voltage and frequency that has been provided or set by a synchronous generator. That's really important. And it's not a sort of A or B. There's a lot of different variations in that technology depending on the scale, but it is an area where we're still early days, and there's a lot of opportunity for innovation if we look at power electronics and power equipment for supporting energy storage on the grid. Next slide, please. And lastly, it's important to note that the future of renewables plus energy storage as the way we generate electricity is going to have to compete with a lot of other alternatives, especially as the penetration increases. The economics for renewables plus energy storage are going to become more and more challenging, and the competitors, whether they be demand response or conventional generation with carbon capture and sequestration, the use of renewable fuels, or nuclear, even just overbuilding and allowing increasing amounts of curtailment, and of course, transmission capacity. These are all other ways of helping to solve this challenge of intermittency and electrification. In reality, we're going to probably see a mix of many of these when it comes to the grid of the future. And where that line, that transition line lies between, how far do we get with renewables penetration, and to what extent do we need dispatchable generation to fill the remainder is to be seen. And that's going to be driven a fair bit by economics. Next slide, please. All right, so what does this mean from British Columbia? I'm going to take about half of these slides and turn it back to Seb. I think that nobody's going to be surprised to see a chart like this. British Columbia's grid is driven especially by hydro generation, and that's a really fortunate place for British Columbia to be. The flexibility and the environmental characteristics of hydro generation are a real advantage, allow for British Columbia to effectively have a very close to zero carbon grid. And the flexibility of that grid has allowed BC Hydro in energy trading to make a lot of money for British Columbia residents over the years, because it can be that adaptive generation source on the grid in a system that connects with all of Western North America. That said, as we look towards the future, BC Hydro has identified there are going to be challenges in the network. And one of the areas that is particularly important is going to be the transmission constraints. So a lot of this hydro generation is located in areas that are not close to centers of demand, which is the South Coast in British Columbia, and it's brought in by transmission lines. And as we move towards electrification, we're going to see increasing strain on the transmission system, which is going to require investment. In the next slide. And so the big opportunity here as we look, and BC Hydro's got a call for power out, is that as we potentially have renewables coming in, variable renewables, wind and solar coming into British Columbia in an increasing level, the hydro system is going to be able to adapt and absorb the intermittency from an energy point of view, big picture, kind of even up to seasonally. The challenge is really more so about how do you move that energy into where the centers of demand are and the constraints on transmission lines. And so BC Hydro has announced the intention to deploy 600 megawatts of storage, and really that primary application is transmission support. It's being able to charge that energy storage in the lower mainland when there's less load on transmission capacity into the lower mainland, and then use that energy storage to meet peak demand in addition to the transmission system when it's needed. That's the first steps, but we can certainly already see that electrification is going to mean increase in stress in other areas. And in all likelihood, we're going to see more opportunities for energy storage in British Columbia going forward. So, in the distribution system, as we look at increasing levels of electrification of heating and electric vehicles, that puts load into the distribution system, and opportunities for energy storage to help defer investments and to help provide support to that distribution system are almost certainly also going to be there. So where we won't be seeing in British Columbia is the big picture energy arbitrage opportunities, but the transmission and distribution network support and ancillary services may be increasing opportunities. And one of the note is, we talked about competition. It's interesting to point out that Fortis, in looking at their resource plan in 2019, identified did quite a bit of comparison between alternatives and identified renewable natural gas as being a lower cost route to increasing the amounts of energy storage. Now, it should be said a lot has changed in energy storage since 2019, and so the conclusions that they reached in that report, may be different based on today's data. But it is interesting to see how those competitive factors are already starting to be evidenced here in British Columbia. All right, Seth, back to you.
Thanks, Michael. That was a great overview of the global opportunity and how that translates to BC. Looking at the BC's energy storage value chain and trying to map it out, there are several trends that pop out and are apparent. BC obviously has a lot of natural resources that contribute to the upstream segment of the supply chain. However, our strongest assets are our people. BC has robust expertise in areas such as exploration and mineral extraction, but also hydrogen technologies and development of advanced power electronics and systems. So a lot of the innovators in BC are either pre-market or in the initial phases of deployment, and they need to scale. This scaling is crucial for them to be able to compete globally with lithium-ion producers. And to support this, CIC looks at innovation in a very broad sense. This includes not only solutions that address technical challenges, but also novel and innovative business models that can deliver value and reduce GHG emissions at the same time. And with that, I'd like to conclude our report review and introduce Lara Depla, who will help us tackle some of the questions that were raised. Lara?
Thank you, Sepper. Hey, everyone. I'm Lara. I'm a clean energy analyst at CIC, and I will take us through the Q&A session of today. Feel free to submit additional questions through the Q&A function of Zoom, and we'll try to address as many questions as possible. If there are any questions at the end that are remaining unanswered, please feel free to reach out to us over email, and we'll try to address them afterwards. We'll dive right into it with the first question on storage applications for industrial heat. So the question to Sepper and Michael is, what could be the role of energy storage for the decarbonization of industrial heat in hard-to-abate industrial processes? And what are the leading technologies in this space?
So the energy storage is, as mentioned, is a real opportunity, I think, for thermal energy storage. It's early days yet, so to talk about leading technologies is probably a difficult thing to say at this stage because we haven't seen a lot of deployments. That said, most of the higher temperature energy storage, thermal energy storage systems, if you look at industrial applications, are going to be based on heating up of solids. A lot of the kind of box of rocks, to put a crude name on it, but whether it's gravel, crushed stone, or sand, or bricks, you're seeing a variety of those sorts of applications. And the big advantages there is just the cost of the energy storage media is really, really low, right? Sand is pretty cheap by and large. And as mentioned, you can charge these with resistive heating, and so the charging process is almost 100% efficient. The challenges you have to look for from an innovation point of view with a lot of these is looking at heat transfer. So, if you think about a big rock, you can heat the outside up and it gets hot, but the inside takes a lot longer to heat up. And so the speed at which you can get energy into and out of those systems is going to be important. And then the mechanisms they use for heat transfer in and out of the energy storage system are going to be important for different applications. So depending on which industrial application you're looking at, those are going to be some of the economic drivers. I don't know, Sep, do you want to add to that?
No, I think you answered it quite well.
Okay, thank you. In the presentation, there were different energy storage applications and use cases shown over the next year or so. What would be the key energy storage applications with the largest potential in BC for the next 5 years?
Yeah, BC Hydro is looking at energy storage for transmission support, especially when you think about the 600 megawatt call that's been put out there. I think they have their eyes open towards other roles within the network. And broadly speaking, we're talking about grid support as being the primary applications, as opposed to really being needed to help integrate renewables in British Columbia. And so, the batteries it's likely batteries that are going to be deployed to that 600 megawatts to be located in transmission grid support. But you may see applications open up as well in supporting voltage regulation, frequency regulation within the distribution system. As that moves forward, I think it's early days for British Columbia. I think they recognize that. So the 600 megawatts is a starting point, but probably not an end point.
I just would like to add that BC Hydro just recently released an incentive program for energy storage for really anyone, even the small businesses, to really on the demand response side of things, where the batteries will not be exporting to the grid, but they will be controlled by BC Hydro, and to be able to essentially reduce the load and take off the load and put it on the battery. So do check out the energy storage program that came from BC Hydro. I think they cover up to almost 80% of the project cost. And I think this is an area where we're going to see a lot more as BC Hydro is trying to ramp up demand response program.
Thank you. In terms of using energy storage for transmission and distribution deferral, there was someone wondering how challenging it is to actually implement energy storage systems into the transmission and distribution system.
Well, I think there's good evidence of it being done quite a bit already. So I don't know that it's necessarily something that is significantly challenging. I think you do need to obviously look at constraints around the voltages that you're going to be operating at, but power equipment is pretty good at doing that. And so right now, I think that, that generally is solved in terms of a technological challenge, and really it's able to be deployed right now.
Yeah, I think I would just add that if you look at the numbers coming from US, almost half of the deployments are for the transmission and deferral programs.
Mm-hmm. I do think that in the distribution system, there's probably more opportunities for innovation. When you look at, there are regulations in the United States now that in some jurisdictions where they're requiring what are called smart inverters, where you've got some capability for voltage regulation in the inverter, where you've got rooftop solar or residential energy storage systems. Now that I think is an area that is keep an eye on that space. There's a lot of technology in the grid today, which is there for protection to deal with transients in the grid, and any new energy storage systems relying on inverters are going to have to work with that and their IEEE standards and so on to develop. But this is an area where there's active technology development.
Okay. There were different battery storage technologies mentioned in the presentation, and one of them were vanadium flow batteries. Someone is wondering, what is the potential of vanadium flow batteries and what needs to be established in terms of supply chain for them to have success or to be successful?
Vanadium flow batteries are one of the leading contenders for some of the, especially this kind of intermediate duration right now. So if you look at kind of the technologies that could potentially become long duration energy storage support for integration of renewables, vanadium flow batteries, and we have one of the leading companies in British Columbia and Infinity. They're one of the leading options for that. The challenge is, of course, that with any of these technologies, including flow batteries, is the volumes that they're being produced are still relatively small scale compared to what's going on in lithium batteries. So they're at the stage where they need project wins and they need to find markets, or they need policy support to get into those early demonstrations of 8, 10, 12, 16, 24-hour. Transmission support may be a good market for that. The transmission support applications are not necessarily just short duration. I think if you were to talk to utilities like BC Hydro, they'd indicate that longer, maybe better, especially if you've got a winter peak utility like British Columbia. And so, looking for market opportunities that allow for scale, as we talked about in the report, is going to be really critical for vanadium. I wouldn't want to speak to the supply chain in terms of mining for vanadium. That's kind of beyond my realm of expertise. Sorry.
Okay, thank you for answering that question. Another question that came in relates around long duration energy storage systems. Could you maybe elaborate on what is the potential of long duration energy systems? And also there was a specific question related to how long duration energy systems could fit into microgrids in BC. If there's any role for them in microgrids.
Yeah, so we didn't talk about it, but that is another area in British Columbia that I think there is an opportunity for energy storage, is what are called non-integrated communities, or communities in British Columbia that may be connected by a weekly connected to the transmission system. Maybe they have one line going in. Sometimes these are microgrids already, or there may be potential for microgrids. So, that's definitely an area for energy storage within British Columbia, and broadly speaking, to play a role and there are good examples in maybe slightly larger communities. If you look at island communities, for example, there's an example we use in the report of St. Eustatius in the Caribbean, which has almost entirely gotten itself off diesel generation by using solar and wind and grid forming inverter technologies on a battery storage system. And the durations there definitely are going to be more than 2 to 4 hours, potential. That's where you're going to want, especially for communities that may face longer outages in renewable generation. That's where you're going to want to see longer duration energy storage systems. Broadly speaking, the big market potential for energy storage, I think that can be as big as the a very large market, but it's really going to depend on driving costs down, and we're not there yet. So it's the combination of renewable penetration going beyond 70 to 80% with energy storage that's going to extend to weeks or longer, sort of quote unquote seasonal energy storage. To do that, energy storage systems are going to have to demonstrate the ability to get a lot lower in cost. And if they can, then we could see very large opportunity. But that's really the big challenge, and that's where new technology is required.
And I would just add that, again, looking at U.S., DOE has, Department of Energy in U.S. has identified long duration energy storage as one of the biggest challenges, because today with lithium ion, we really can't get, projects that are economical or bankable, anything over 4-hour duration. So when you're looking at, really long duration, like 12 hours, 16 hours, more than that, we really need alternatives. And vanadium is one of the contenders in this space. Also, compressed air is another one where industry is looking really deeply and seeing how can we deploy longer energy storage duration and be able to bring down the cost to be able to compete with lithium.
Okay, thank you for answering that question. Another question relates to the role of EV batteries for inserting electricity into the grid. What are your thoughts on the future of vehicle-to-grid initiatives and also the usage of second life EV batteries as energy storage?
Those are kind of two different things. Maybe I'll take the second one first. So second life EV batteries, I think there's certainly a big opportunity there. Batteries for EVs, kind of are at their end of life from an electric vehicle point of view when they've still got maybe 70 or 80% of their capacity left. And so reusing those batteries is clearly an opportunity for the grid. The challenge being that these are used batteries, so they're potentially lower cost, but they've got to be integrated in ways which are different than what they were designed to do, and they've got to be run and operated in ways that are different what they're designed to do. And so that goes to financing, insurance, and all kinds of kind of non-technical challenges that also go there. But the opportunity is huge when you step back and you think that there are 10 times more batteries being produced for electric vehicles than for the grid energy storage, then clearly there's going to be an opportunity for reusing some of those batteries in grid applications. So that that's a really interesting opportunity. There are business hurdles that need to be overcome, but that's an area where innovation may be able to help, and it's a one that's bright. The vehicle to grid one is a different challenge entirely. And again, though, if you think about, look, all this energy storage is driving around and is located in the cities, can't we just tap into it? Yes and no. There's behavioral challenges that have to be overcome. People come home, they plug in their car, they want to believe that it's going to be charged when they go. So maybe you can tap 20% of a homeowner's vehicle capacity, and they would be fine with that. Of course, they need to be compensated for that. There are challenges with the automotive manufacturers. You're going to introduce extra cycling on those batteries, and these are cars that are going to be under warranty, for example. How does that affect it? So there's some business hurdles that need to be overcome. I think one of the areas you may see vehicle to grid take off first is going to be when you look at fleet vehicles. Things like school buses, which are driving around the city during the day, which is not a period of peak demand, but are at the end of their use and plugged in at night during periods of peak demand. And if there's charge available in those fleet vehicles, then it's probably an area where it's a lot easier to manage. So, kind of look to those areas, I think, as places where vehicle to grid may be able to take off and demonstrate its capability. EV management, charge management, whether it's through passive systems or whether it's active systems, I think is going to be incredibly important to deal with electrification and potential impacts on peak demand. So, even if it's not just, charging the grid or using the battery storage in the vehicles to supply energy to the grid, just the adjusting of the timing of when those vehicles charge is going to be absolutely critical. And certainly there's an opportunity there in terms of the technology that enables that.
Okay, thank you. We're almost running out of time. We'll try to address one or two more questions. Someone has noticed that in the report, compressed air energy storage has been listed as a high efficiency and long duration storage option. Could you potentially elaborate on the big challenges in deploying compressed air energy storage and what would need to happen in order to make this storage solution more viable?
So compressed air energy storage traditionally has been a relatively low energy efficiency storage. So it was pumped underground, but heat from compression was discarded. And then natural gas combustion was used to preheat the air before it was driven through. And so the biggest compressed air energy storage systems in the world, that's the way they operate. And so the net efficiency, as you can imagine, is quite low, and it's definitely not a zero carbon. So the more advanced energy storage, compressed air energy storage systems actually then capture the heat during compression and then reuse that heat to preheat the air before driving it through a turbine. And that certainly gets rid of the carbon emissions, but also improves the overall efficiency. The key to cost-effective competitiveness, arrives around those things. And below ground, the volume of the energy storage, the cost of the energy storage medium, if you want, is a lot lower than doing so in above ground tanks. And so, the geology where you can deploy compressed air energy storage is really critical. And it's by no means limited. There's a lot of places where you could do this. But that's going to be a big determinant in terms of the economic and the competitiveness of compressed air energy storage.
Okay, there were a lot of questions also around if the hydropower in the BC grid reduces the need for energy storage systems. I think this was already addressed in the presentation, but maybe a follow-up question on that. It also appeared in the Q&A. Is the question around, is there any opportunity for integrating energy storage systems with hydropower?
So yes, the variety of different ways. I mean, you can obviously put a battery system adjacent to and take advantage of the grid connection that is located at a hydro generation facility. And what that may do is provide things like ramping support, right? You can turn on a battery and have it start discharging very, very quickly, where it may take a minute or two to spin up additional turbine capacity in a grid storage or with a hydro capacity. You can also take existing hydro facilities and turn them into pumped storage, pumped hydro storage hydro facilities by putting the water back uphill. I mean, that sort of seems obvious, but it's obvious. It's another route that you can go. Although with a large network like British Columbia it's not necessarily needed. You can just let the water build up behind the dam, as opposed to putting water back uphill. That large network of dams really does provide British Columbia a lot of opportunity to integrate renewables without needing battery energy storage to do so. As we talked about in the grid, it's other applications in British Columbia which are going to be important, but are really going to drive the need for energy storage in British Columbia.
Yeah, I just want to add that in some of the examples we've seen, hybrid solutions with dams, we see other technologies that are not battery. For example, supercapacitors, because they're much designed for much shorter duration, and by just pairing them up with an existing facility, now they're able to participate in markets like frequency regulation, where previously the ramp up time for the dam or hydro facility would be too slow to participate in such a market.
Okay, then maybe as a very last question, maybe we can have a short answer to this one, is if you compare lithium-ion batteries versus other new battery technologies, do you expect that mostly the cost of the lithium-ion batteries will go down, or do you anticipate these new technologies kind of being able to compete with lithium-ion batteries?
Oh, I think the answer is yes. That the cost of lithium batteries is going to continue to go down, and that is a challenge, especially for new technologies that are trying to win market share today. But really, the big question is, where's the tipping point? At some point, it's going to be less competitive. Lithium-ion batteries are becoming less and less competitive as you get towards longer duration, and these newer technologies are going to see an opportunity. And the sooner they can start to win projects and get scale, and the sooner those new technologies can, get manufacturing going and all those learning curve benefits of higher and higher volumes, then the more competitive they're going to be. So, this is one of the comments in the report, is that if we look at innovation, it's not just about, say, energy density in a battery that is critical. It's also looking at all the different ways in which innovation can help new technologies start to win projects and achieve that scale. That could be manufacturing innovation as an example. So that there's a lot of different ways which innovation can play a role in helping those new technologies get into the market and start to achieve that scale that they're going to need to compete with the continuing decline in lithium-ion battery costs.
Thank you very much, both Sepper and Michael, for answering all those questions. I will pass on back to Sep.
Thanks, Lara. If you're an innovator on this call, or if you're watching this video later, we would love to hear from you and your projects and see how we can help you. If you're an end user or a stakeholder, we'd love to learn about your challenges and the barriers that you come across when you're trying to adopt these new technologies. If you have any outstanding questions, feel free to reach out. If you haven't been able to read the report yet, it is available for download on our website. Thanks again, and we'll have the recorded version and the slides ready for sharing in the next 24 hours.